Hi guys, today I'll show you how to solve this Waterloo math contest problem from the grade 10 Cayley contest. This is an extremely difficult problem that I think should really appear on the final exam of second computer science rather than a grade 10 math contest. And to be honest, I couldn't solve it without the help of a hint. So if you're curious, then stay tuned. I'm going to give you a detailed step-by-step explanation on how to solve this counting and probability problem. This is question number 25 from year 2016. It says a new language only uses the letters A, B, C, D, and E. Letters A and E are vowels, and B, C, D are consonants. A sequence of letters is called a word if it does not include the same letter twice in a row, and it does not include two vowels in a row. So for example, A, B, A, and B, C, D, A all follow or satisfy the two conditions stated. How many words are there in this language that are 10 letters long and begins with a vowel? Now let's explore this 10-letter long word, right, using the help of a tree diagram. So we know that the first letter has to be a vowel, right? And there are two choices for the vowel, A and E. Now what about the second letter? The second letter has to be a consonant because the rule says that no two vowels can be together, right? And you can pick any consonant to be your second letter. So there are three choices for a second letter. Then together, for a two-letter long word that begins with a vowel, you have 2 times 3 equal to 6 choices. That's the multiplicative law, right? Now what about the third letter? Now it starts to branch off, right? Your third letter can either be a vowel or a consonant, right? If it is a vowel, then you can pick any of the two vowels, right? So there are two choices for the vowel. Then the consonant, if you want your third letter to be a consonant, you just cannot repeat the same consonant you just used for the second letter. So therefore, you're left with two choices, right? So far, for a three-letter word that begins with a vowel, you have 24 choices. Now, what about the fourth letter? Okay, that's going to branch off even further, and it's going to depend on what letter you chose for the third letter. If your third letter was a vowel, then your fourth letter has to be a consonant, but it can be any consonant, so there are three choices. If your third letter is a consonant, then your fourth letter could be a vowel as well, and there are two choices. And if you choose your fourth letter to be a consonant, that's also fine. You have two choices for that consonant. And some people might ask, okay, why are there two choices, not one, right? Because you said you cannot repeat, right? Okay, it's not three, definitely, because you cannot repeat. And it's also not one because your fourth consonant, right? The consonant in the fourth letter could be the same as your consonant in the second letter. So therefore, you have two choices for this consonant. Now, what about the fifth letter? Okay, this branching is starting to get crazy, right? And if you sum them up using the additive property, then there are 312 choices. And if you go on to the sixth letter, then the number of choices start to grow almost exponentially. So at this point, I realized that, okay, that's way too many branches. There's no way I can continue drawing this tree diagram to the 10th letter, although if given a big enough sheet of paper, I could, but that's going to be very error prone. So I decided to change my strategy. I want to identify the pattern. And I know that it has to be a recursive pattern because I realized that the next letter is going to depend on what my current letter is. Now, let's try to find this recursive pattern. Let me introduce two new notations. Let VI be the number of I-letter words that start with a vowel. Let CI be the number of I-letter words that start with a consonant. So for example, C2 is the number of two-letter words that start with a consonant. V10 is the number of 10-letter words that start with a vowel, and this is what we're looking for. Now let's go back to the beginning of the tree and try to look for some recursive pattern. The first letter has to be a vowel, right? So this is essentially a one-letter word that begins with a vowel. And we know that V1 is equal to 2. What happens as you introduce the second letter? The second letter has to be a consonant, and it begins with a vowel, right? So this is essentially a two-letter word that begins with a vowel, right? And you can see this as a one-letter word that begins with a vowel, V1, followed by a C1, right? And we know that C1 is equal to 3. What happens as you introduce a third letter? You see, you can see V3 as a V1 followed by a C2, right? And the problem is, how do you express C2, a two-letter word that begins with a consonant? Well, C2 can be seen as okay, a one-letter consonant C1 followed by two branches, right? One of the branches is going to be a V1, and the other branch is kind of a special case of consonant where you cannot repeat, so it has only two choices, right? Now, what happens as you introduce the fourth letter? We see that V4 can be similarly defined as a one-letter vowel word, V1, followed by a C3. And you can define C3, or the number of three-letter words that begins with a consonant, as a one-letter consonant, C1, followed by some kind of branches, except this time is slightly complicated, right? It is going, so on the lower branch, you have essentially a two-letter word that begins with vowel. So on the lower branch, it's V2. On the top branch, it is actually a non-repeating consonant, right? Then followed by a sub-branch of one-letter vowel, right? And on the top branch, it is a non-repeating consonant. So we can see C3 is essentially equal to C1 times V2 plus 2 of V1 plus 2. And of course, you can start to see the pattern in the fifth letter, right? In a five-letter word, it's essentially a one-letter vowel, V1, followed by C4, a four-letter consonant, right? And of course, you can define C4 recursively, using the similar kind of decomposition, right? C4 is essentially a one-letter consonant, right? Followed by a lower branch of three-letter word that begins with vowel. So C1 followed by V3 on the bottom branch. On the top branch, it starts to get a little bit more complicated. You have a V2 in the first branch off there, and you have a V1 in the final branch off there. So C4 is essentially equal to C1 times V3 plus 2V2 plus 2V1 plus 2, right? So if you summarize everything you have together, you start to see the pattern, right? For V1, V2, all the way to V5, it is actually fairly straightforward. Just simply a V1 multiplied by C1, C2, C3, C4. The C1, C2, C3, C4s are a little bit complicated. You see, it has many layers of brackets, right? So, but nonetheless, this still works. If you really want to use this to find C9 and V10, right? Because V10 is simply going to be V1 times C9, right? You can do this. However, I'm just going to take an extra step or an optional step to simplify this, all these brackets into something, I guess, more flat and straightforward. So I start to see that, right? There's a part from the previous CI, right? That's always appears in the next CI. So for example, in C3, right? We see a part that's V1 plus 2, and that actually appears in C2. So that means I can replace V1 plus 2 with some expression of C2, right? So I'm going to rearrange it. So C2 divided by C1 is essentially equal to that part that appears in C3. So therefore, whenever I see V1 plus 2 in C3's definition, I can replace that with C2. And if I rearrange it, I have Cn is equal to C1 times Vn minus 1 plus 2 over 3 C of n minus 1. So this is a recursive definition that depends on the previous C term. Okay, so now I have my kind of rearranged definition that's a little bit easier to work with. I can find any Vn, I can find any Cn because I have an initial value for V and an initial value for C. And if I do carry out this calculation recursively, there's no other way, after some tedious calculation, I get V10, right? And which is 199,776.